So today the date is 23rd October and this is week 13 lecture. So I'm just giving the heading week 13. So let me start. So today we will mostly deal with uh, thermal problems. Like let's say we have some temperature given and due to that there is expansion in the body. So we will deal with such kind of problems and also some bending and twisting kind of problems. So my name is Shubham Rai and I am a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So this is an extra session for you. And this is for 1 hour. So let me start. Hope you are able to hear me. So let me just start it out. This is a new thing for me. Okay. So I will start with problem one. Okay. The problem one says the dimensions of an overhang crank and overhang crank are given in figure. The force P acting at the crank pin is 1 kilonewton. Now the crank is made of steel whose yield stress of the steel is given to you. Yield stress in tension. So that is 400 Newton per mm square, 400 megapascal. So that is the yield stress and the factor of safety is 2. Okay. So what you have to do is you have to using maximum shear stress theory. Theory of failure. You have to determine the diameter. I'll draw the diagram and I'll tell you which diameter you have to determine. So you have to determine the diameter D at section XX. Okay. So let me just um, okay. So We go down. Or is it not going down? Let's wait a minute. This is something new for me, so now I can. And now it's fine. Let me investigate this. The diagram something looks like this. Okay. So here you have, let's say this is the crank. This is overhand crank, and this is the crank, part of the crank pin with where the force is acting. And here you have an extension. So, and you have to determine the diameter at this section only. Okay. Let's say at this point, and this point is given by the section. This is section XX. Okay. And here you have you have a point here, and force is acting let's say, out of the plane or towards in inward direction to the plane. So it is not acting in this plane, rather it is perpendicular to this plane. Okay, so now if I draw the side view of this, so it will look something like this. Um, Let me just draw. So let's say here I have a central line, and here also I have a central line going on, and from here also there will be a central line. Okay, so if I draw this, it will look something like this. So here you have a hole, and here also you have a hole. And let's say here you have a force acting. Here you have force acting. Now, since this is a side view means you are looking from this side. Okay. So when you're looking from this side, it is like this. And now your force is visible to you because um, that is acting like this in this plane. Okay. So this is the front view that we have drawn on the left hand side, and then this will be the side view. If you look from this side, it will be this side. Okay. So here you will get this force that will be acting. So now let me draw the distance. Are you getting it? So this force is acting here at this point. Okay. In perpendicular to the plane. It is acting perpendicular to the plane. Okay. So that's why it's visible in the side view. Now let me draw the distances. So distance will be, so this distance is um, from here to here. You have a distance of 50. So this distance is 50. And this distance, let's say this point P, and this is also point P. And this distance here is 500. I start from this point and go up to this point. So this distance is 500, and all are in mm. So, and from this point to this point, it is So this distance is 100, and from this point to this point it is 25. Okay, and this diameter here is, let's say, d. And this diameter only you have to determine. So how will you do this problem? So it is a case of bending and twisting both, because the force which has been applied at the point P, uh, and forces in direction, forces outward to this plane, forces acting in a direction which is outward to this plane. So what it will do at point this, at this cross-section XX. So due to this force in this shaft whose diameter is d, so in this shaft there will be a twisting. So since this is the shaft, let's say, and here you are applying a force, so there will be twisting of the shaft. And then due to this force, there will be bending also, because force is acting in this direction. So at this point of the shaft, there will be some reaction due to this force, and this reaction will act like this, and it will bend the shaft. It will do bending also and twisting also of the shaft. So here we have both bending and twisting in this shaft which has a diameter d. So let me do the solution. This pen is not working exactly. Um, let's wait. This pen is not working. So can you try to solve? Meanwhile, can you try to solve this question? Please try to solve this. Let me. Yeah, please try to solve this question. Oh, now it's working. I don't know. Okay, so let me just solve this one. So this is the solution. So force given to you is 1 kilonewton, right? And yield strength that is given to you was 400 MPa, so that is 400 Newton per mm square. And factor of safety given to you was 2. So now you have to find firstly the permissible shear stress. So permissible shear stress will be, so this will be, now you know that the maximum stress, so in a uniaxial test, tensile test, the maximum stress induced in that specimen is half of that yield strength. So yield strength in tension. So that's why if we, so if we take maximum shear stress from there, so it will be half of this yield strength. So let me just write, so maximum yield strength, maximum shear strength, or maximum shear stress, that will be half of this yield stress. This will be 0.5 times 400, which is 200 Newton per mm square, right? Now, let's say, so now you have to determine maximum shear stress that you can allow. So it will be this yield, or maximum shear stress divided by factor of safety, right? So this will be 100. So you can only allow 100 megapascal of maximum shear stress in the body, because you have to give a factor of safety of 2. Okay. Now, so as I told you, there will be both bending and twisting at the cross section XX. So here there will be both bending and twisting at cross section XX. So we can just write. I'm just writing it. So here the section X section of the crank pin at XX is subjected to combined bending and torsional moments. Okay. At the section XX, bending moment, bending moment. What will be bending moment at the section XX? Can you tell me? So bending moment here will be at the section XX. So this force P is acting. And what is the distance between the shaft and the force P? So can you tell me for bending, what is the distance? It will be 100 plus 25 plus 50, right? Because here, let's say there is a section XX. So here there is section XX. And here the force is acting. This force will do bending of this shaft. So this is the shaft, this will do the bending of this shaft in this direction. So distance you have to measure because moment is a distance between point at which you want to measure moment and the line of action of force. So distance between that. So this distance is 100 plus 25 plus 50. So this much amount of bending moment will be introduced. So let me just write. So bending moment. So it is 1,000 times. 1,000 because 1 kilonewton force is acting. So this is P. 1,000 times 50 plus 25 plus 100 because this is the distance between section XX and line of action. I mean at the point. So this is the horizontal distance between section XX and the point where the force is acting. So if you calculate, this will be 175 times 10 raised power 3 Newton mm, right? Because it was all in Newton per mm square. So this is in Newton and this is in mm. So it will be Newton mm. Okay. So and then you have to find torsional moment also. So let me just write torsional moment MT is given by what will be torsional moment? So that will be given by for torsional moment you have to take vertical distance between point P and this axis of the shaft. So that is 500, right? So P into 500, that will be the amount of torsion. So let me just write. So this will be divided by MT. So this will be 1,000 times 500. You can just simply write 500 times 10 raised power 3 Newton and okay. Now you have um, this torsion moment. Now you have to find stresses due to both of these, and and then you have to find shear stress. So stresses due to bending moment will be tensile stress, and stress due to torsion will be shear stress. And then you can draw a Mohr circle, and combination of these two stresses with the combination of these two stresses, you have to find maximum shear stress. So that will be radius of the Mohr circle, and you have to equate that maximum shear stress equal to the permissible stress, and then that maximum shear stress that you will obtain from the Mohr circle. So that will be in terms of diameter of the shaft. And then when you will equate equal to permissible shear stress, you will get the diameter. So let me just find the stress due to bending. So stress due to bending is, let's say I'm denoting at sigma xx, uh, and let's say this is sigma b. Sigma xx because it is acting on cross section x. So let me just write only sigma x rather than sigma xx. So this is a tensile. I mean, um, this is, you can say that tensile stress because we have been given strength in tension only. Anyway, in tension and compression, it will be same here because it is isotropic material and shaft diameter is same. So anyway, so let me just write stress will be same. So it is bending stress. So I'm saying sigma b. So this will be the formula for bending stress is bending moment into y by I, and y will be the maximum distance. So that will be the radius of the shaft, which is d by 2. Diameter of the shaft divided by 2. So MB is 175 into 10 to the power 3. So this is Newton mm, and this is d by 2. So d, let's say we have in mm, and uh, I will be pi by 64 d to the power 4, right? So this will be Ixx. Okay. So you know that, I mean, which I it means when this group writing. So pi by 64 d to the power 4. So finally, what will you get is you'll get 1782.54, okay, times 10 to the power 3 divided by d3, because 1d in numerator will cancel and you will be left with d to the power 3. So this unit is Newton per mm square. Okay. Now let's go ahead. So let's calculate the shear stress due to torsion. So shear stress due to torsion, what is the formula? So you know that it is the twisting moment multiplied by maximum distance, which is d by 2, and divided by polar moment of inertia j. So polar moment of inertia will be half of this moment of inertia that we have taken in bending. So then mt is again 500 into 10 to the power 3, and here we have d by 2, and here we have pi by 32. Instead of pi by 64, we have, sorry, it will be double of polar moment of inertia will be double of what we have taken in bending moment. So it will be pi by 32. This is nothing but perpendicular axis theorem. So Ixx plus I pi by is equal to Izz. So Izz will be twice of Ixx because Ixx is equal to I pi by. So, so here we have written Ixx, and so this will be twice of this. So okay, so pi by 32 d to the power 4 it will be, and when you calculate, so it will be 2546.48 times 10 is power 3 divided by dq. Okay, so you have Newton per mm square. Now, maximum shear stress. What will be maximum shear stress? So using these normal stress and shear stress, you can draw more circle, and you know that radius of more circle will give you maximum shear stress. So maximum stress is given by, so you have term x here, which is nothing but sigma x by 2 the whole square plus tau square. Okay. So just put the values. So finally, if you solve these expressions, you just put the expression of sigma x here and divide by 2 and then tau and then square and then take square root. So finally, you should get 2697.95 into 10 to the power 3 and divided by dq, Newton per mm square. Okay, because this is stress. And then you equate this equal to a maximum permissible shear stress. So because we are using maximum shear stress theory, so I'm just writing here. So using maximum shear stress theory. So what will you get? You have to equate this to 697.95 into 10 is power 3 divided by mu cube. This should be equal to 100. And finally, when you solve, so you'll get d is equal to 29.99 mm. So it is approximately equal to 30 mm. This will be your answer. Okay. So that's how you have to perform calculations while designing something. You have to consider all the stresses acting, and then you have to decide a suitable failure theory. And then the stresses that those will be acting will be in terms of the dimensions of the component. And then you will equate that expression equal to the expression that you get from failure theory. And from there, you'll get the dimension of the component. So let me, as I told you, let me go to some problem which involves temperature. So I just want to take some interesting problem. Let me take one problem which is related to temperature. Let me take problem number 2. It says the rigid bar ABC. I'll draw the diagram, don't worry. In figure shown here is pinned at B. So it is pinned at, there is a rigid bar which is pinned at point B and attached to the two vertical rods. Okay. Initially, the bar is horizontal. The bar is attached to the two vertical rods, but bar itself is initially horizontal. And the vertical rods are stress-free initially. What you have to do is you have to determine the stress in the aluminum rod. So there are two rods. Out of that, one rod is of aluminum. So you have to determine stress in that. So you have to determine the stress in the aluminum rod. If the temperature of the steel rod is decreased by, so another rod is made of steel, so whose temperature is decreased by 40 degrees Celsius. Okay. And then you have to also neglect the weight of the bar. You don't have to consider weight of the bar ABC. So let me draw the diagram. So diagram looks something like this. Let's say here Here you have some point. This point B, and it is rigid road ABC. So let's say this road is rigid road, and we have a steel bar and aluminum bar. So this is point A. So at this point, let's say we have this steel bar. So this is made of steel. And here at point B, C, let's say this point is C. We have a aluminum bar. This is made of aluminum. Okay. Now your length of the steel is 0.9 meter. Area area of this road of the steel is 300 mm square, and Young's modulus is 200 into 10^9. This will be 200 gigapascal, right? So this is Newton per meter square. Okay. This is Young's modulus, and then you have thermal coefficient of thermal expansion, which is 11.7 micrometer per meter per degree Celsius. Okay. You have these properties for aluminum, for steel. For aluminum, similarly, you have length of the aluminum is 1.2 meter. Area is 1200 mm square. And Young's modulus for this will be lower, so 17 to 10 power 9 Newton per meter square, and alpha will be 23 micrometer per meter degree Celsius per degree Celsius. So, and here you have 3 points. Um, so this is point A, this is point B, and this is point C. And you have also been given with distances. So this distance from A to B is 0.6 meter and B to C is 1.2 meter. So from A to B you have 0.6 meter, and from B to C you have 1.2 meter. Okay. So this is your question. So rigid bar ABC in figure shown here is pinned at B and attached to two vertical rods. Initially the bar is horizontal and the vertical rods are stress free. Determining the stress in the aluminum rod if the temperature of the steel rod is decreased by 40 degrees Celsius. You have to neglect the weight of the bar ABC. So how will you solve it? Can you tell me? Yes. So let me solve this for you. Again, this pen will take some time. Meanwhile, try to solve this question. What should be your approach? Now you are decreasing the temperature of steel, so it will contract. But then the aluminium rod will not allow it to contract that much. So in the free state, if the steel would have been free, it would have contracted, but aluminum is not allowing it to contract that much. So there will be tensile stress in the steel, right? And um, so, and there will be tensile stress in aluminum also, because when the right hand side due to contraction, then the left hand side, the point A will go in upward direction, point C will come in downward direction. So it will induce tensile stress in aluminum. So there will be an equilibrium point where this bar ABC will be tilted, and there will be tensile stress in steel as well as aluminum. Okay, so let me just find out, and then you have to find stress in the aluminum rod. Okay, so from there we can find, firstly we have to find the force, and then we can divide it by area of the aluminum, we get the stress. So let me just draw the diagram after deformation, how it will look like. So pen is not getting connected. Okay, so how it will look like? Let me know the solution. So let's say this is your point B, right? And this was the initial configuration of your bar ABC, right? Initially it was like this. Now after deformation, it will be tilted. So tilted configuration I'm drawing. So tilted configuration will look something like this, right? This is the tilted configuration of this bar. So now from this point to this point here, this point to this point, this is the uh, this will be the deformation in aluminum, right? This is point C. This was point A, this was point B, and this is point C. And finally, this is on the left hand side, you have this deformation. So this is final deformation in steel. So I am naming this deformation to be delta steel final. Okay, that's right. So this is something delta of steel at final. I'm saying final because due to temperature. So let's say due to temperature, the deformation in this steel deformation in steel would have been higher. So so for example, it would have gone from this point to this point. Let's say this is solely due to temperature. So this is delta in the steel due to temperature. Okay, delta ST. Now, since it is not free, so aluminium is also there. So when this left hand side will go up, aluminium will be stressed, and it will not allow to the road to go in downward direction, right? So in that way, the steel will not be able to contract that much. So there will be less contraction. And it means essentially when it is at, let's say you have decreased the temperature by 40 degrees Celsius. So in free state, it would have been, the length would have been less. Now you are stretching it. So there is some force acting. So that force, which will be tensile in nature, is doing this elongation. So the elongation due to that force will be this much, right? Due to this force P. So I can say that this is delta in the steel only, and due to the force P acting in the steel. Okay, so delta is P. I hope you have understood the concept. Now, these two are symmetric triangles. So we can say that, what we can say, we can say that delta at A, which is delta at A means final deformation. So delta at A, which is also, I can say that delta, my delta should look like delta, not S. So this delta at A, which is also delta at SF. Okay. So this divided by what was this length AB? So this is 0.6, right? Should be equal to this delta aluminium divided by 1.2 because these two are symmetric, I mean similar triangles, right? So from here we can say that delta at A should be equal to zero point 0.5 times of delta of aluminium, right? From here, because this bar ABC is rigid, it's not going to deform. So delta at A finally is delta in steel due to temperature, right? Minus delta in steel due to load. So that should be equal to delta at A, right? So if you finally substitute here in this equation back, so on the left hand side it will get substituted. So you will get delta ST minus delta SP. So that will be equal to 0.5 times delta AL, right? So now if you substitute what is delta ST, so this will be temperature based, so that will be alpha times strain in the rod of the steel, so which is delta T and multiplied by length, so it will give you delta L. So multiplied by length of the steel. So this will give you the delta ST, that is contraction due to temperature, and then this is delta SP, which is elongation due to, so this is elongation due to force. So that this will be given by load. Let's say load acting as P in the steel, and length of the steel is PL by AE. So that will be the, and this is corresponding to steel. So I'm just writing ST here, and this will be 0.5 times PL by AE in aluminium. So this P is acting now in aluminium. So I'm just writing aluminium here. Okay. And delta in aluminium will be only be due to force P. There will not be any role of temperature because we are not increasing or decreasing the temperature of aluminium. So now if you substitute, so finally alpha delta T times L in case of steel, so that this will come out to be 0.4212. So this is a known value, and then you have load in steel times length of the steel, which is 900 mm, and then area of the steel, which is 300 mm, and E in the steel, which is in mm, it will be 200 into 10 to the power 3. So this is in megapascal, obviously, so Newton per mm square. So this will be equal to 0.5 times load in aluminium, BAL, times length, which is 1200 mm, and divided by area. Area is also, I guess, 1200. So let's check. Yeah, so area is also 1200 mm square, and then you have 70 because 70, so 17 to 10 is power 3 Newton per mm square that you get in aluminium. So finally, you will get one relation. So the relation that you will get will be, if you solve this, you will get 28080 minus load in aluminium. So that will be equal to 0.4762 times the load in aluminium. So let's say this is equation number 1. Now you have two variables, PST, PAL. So you need two equations. So other way of finding PST, PAL will be, so balance moment at point B. So there will not be any bending moment acting at point B because this is, and here the rotation is freely allowed. So there will normally not be any reaction in the static equilibrium. the moment due to PST should balance the moment due to PAL. So PST multiplied by distance AB, which is zero point 0.6, should be equal to PAL multiplied by 1.2. So here we can just write, that as per moment balance, about point B. Okay. So we can say that zero point 0.6 times load PST should be equal to 1.2 times PAL. So it means your PST should be equal to twice of load in aluminum. So this is equation number second. Now you have two equations, two variables you can solve. So if you solve, finally, what will you get? So solving one and two, equation one and two for, so you just substitute PST is equal to 2PL in equation one, you will get PST there from there, and then you can find PAL, which is PST by 2. So for PST and PAL, finally what you will get is your PAL. So that will come out to be approximately 11340 Newton. Okay, so this much you will get. Now stress you have to find. So stress in the aluminum rod is given by, so you know that sigma AL, so that will be equal to PAL divided by area of aluminum AL. So it was 1200, so 11340 divided by 1200. So finally you'll get, so this will be in megapascal because it is Newton per mm square, which is megapascal. So it will get 9.45 megapascal. So this much amount of stress that will be developed in aluminum. So that's how you have to solve the problems related to temperature. So if you have two variables, two unknowns, so you can find the one equation you can find by equating strains in some situations or stresses in other situations. And the other equations you can find by moment balance at any point. Or let's say in that case, if you have force balance, then we can use that as well. Here we did not use force balance because you will have force at point B also, and we do not know what that force will be. So although it's very clear because it will be PST plus PAL, and then since PST and PAL are also unknown, so then force at point B will also be unknown. That's why we have used moment balance. So moment of the reaction force passing through point B will be zero. So I'll stop here. Just wait a minute. So I'll stop here for today, and maybe so this is our last class. So whatever doubts you have, you can post on in the comment section of YouTube and also in the course SWAYAM website. So all the best for your exams. Thank you for your attention, and we'll stop here for today.